Thank you. So you can hear me. Thanks for the introduction. So I'm here to talk about troubleshooting data center, end-to-end troubleshooting in data centers. I know you all are aces in troubleshooting networks and data centers, but I will give you some insights when it comes to what are the features and tools that are built into modern switches that can help you with the troubleshooting, but also give an example how you can build a monitoring fabric to do more enhanced troubleshooting. And also, there are other teams in your organization that are interested in the network packet data that actually is produced in the network to do their stuff. We heard from Nokia about DDoS, security tools, but also the application performance monitoring tools. So let's kick off. Skip that one. I really like this analogy about the 6 blind men and the elephant when it comes to highlight the challenge of troubleshooting. They all investigate a part of the elephant. They start to argue and disagree of what the actual nature of the elephant is. And to have access to accurate and comprehensive data is key in troubleshooting. To quickly identify and be able to mitigate the issue is dependent on the quality of data you have. And so also providing data from the network will allow you to work together with other teams, the application team, the security team, to quicker identify issues and mitigate them. So why is troubleshooting today different today? A little bit of history and moving forward. So in the 15 years ago, the data center was built with a traditional architecture of core, distribution, and access. Layer 2 in the VLANs in the access layer, and layer 3 in the distribution layer. The traffic volumes compared to today were relatively low. Most were in and out of the data center. But the important thing is that the applications were 3-tiered, and all of them were hosted in the same data center. So when it comes to troubleshooting, you knew where the servers were, so you could easily connect your Wireshark to do packet troubleshooting in an easier way. So you had a better control of the network path and where the application were hosted. The tools you had was CLI to do device-based troubleshooting, span ports to get the packet data out from the network. In some cases, you had taps for in and out of the data center for some continuous monitoring. And of course, SNMP was the way to get statistics and bandwidth utilization from the network. The data centers of today are way more complex. To be able to scale to the number of servers, to be able to be flexible when it comes to applications that are containerized, that are virtualized. We're building a spine leaf topology with EVPN as the control plane, and we're using VXLAN to create layer 2 connectivity between the leaves. Of course, the east-west traffic has increased, so it's a lot of traffic inside the data center. But the challenge here is basically that applications are distributed. They are containerized, they are virtualized. Some of the application is maybe hosted in the cloud. And on top of this, we're adding an overlay. We're tunneling the traffic from leaf to leaf using VXLAN. And so we actually do encapsulation and decapsulation of traffic. So it's harder to troubleshoot a network like this. So what are the features built in to modern switches that can support us with troubleshooting this kind of networks. Where should we connect and capture traffic to feed our application performance monitoring tools and network performance monitoring tools with the network data? How can we build a universal monitoring fabric to support all the needs we have for troubleshooting? Polling devices using SNMP is not good enough. It's insufficient for modern for monitoring modern data centers. The network operations need to have access to real-time data that is streamed from each device, not only to have a good real-time view of each device, but have a good view of the complete network. And streaming telemetry is the answer to that. It basically streams every event, every state change, everything that's happened in a device to a central collector or a network management system. With access to the real-time data, the network operators can quickly identify the issue and correlate it with other things that happens in the network. And it's streamed to time series database. And why is that important? That's important because that will also give us the possibility to go back in time to compare now and then, back in time, 1 week, 2 weeks, 3 weeks. Because when you are hit with an issue, that's probably not an issue that happens right now if there isn't a major issue. But you need to go back in time. So streaming telemetry to a central location, to a central database, is key. As an example, to illustrate that polling is not good enough, if there is an interface going down on a switch, if you're using polling, in worst case, you will not identify that issue 5 minutes later, if you have a poll interval of 5 minutes. With streaming telemetry, there's an event generated directly, which is streamed to your network monitoring system. Other benefits with streaming telemetry is that you're building there's a large volume of data streamed to network data lake. And that network data lake is not only used by the vendor management system. It can be the data can be accessed from third-party applications, like a lot of them out there today that can use the data for their purpose. And all of those systems have built-in ML and AI. This is the only time I would say AI in this presentation. So to basically to do forensic, to find patterns, to detect anomalies, and do baselining. So the key is the data, and the key is to have the right, accurate data. Another next feature is Inband network telemetry. To identify latency issues in a larger data center it's hard. And to define it by hop, it's even harder. You can of course see the latency of a flow in the data center, but where did actually the congestion happen, at what device? What device add the latency to this flow? Inband telemetry is designed to provide a deeper information to the packets to be able to troubleshoot latency issues. Actually, Inband network telemetry, I call it INT, at each switch, it inserts a int packet of metadata before it's forwarded to the next switch. And the next switch does the same. At the end of this flow, that metadata is sent to the collector. I have a clicker. So this is what it can look like. There is a flow passing through 6 switches. To the right, you can see information about their path record, ingress interface, egress interface, average latency latency through that switch, minimum latency, and maximum latency. And in this flow, you can also see that we identified a packet drop at the next last hop. So this provides more and granular information than a typical S-flow does, and with a hop-by-hop latency, which is important for troubleshooting. How do we catch the performance killer? Microbursts. When troubleshooting latency issues, you have probably come across that you can see that you have packet drops on an interface, but the utilization is only 10% of the interface. So to catch microbursts, there are bursty traffic, like we take storage as an example, that are very bursty in a very short time. So to catch this bursty traffic, the standard tool that exists in switches are not good enough today. So we need something with a granularity to monitor the buffers and the queues. And that is latency analyzer. Latency analyzer is a hardware feature built into the ASICs. So it monitors the queues. You, as a user, define threshold, a max threshold and a minimum threshold. When the traffic exceeds the maximum threshold, the stats are sent to your monitoring system, and that's why there's real-time streaming telemetry is important, so you get notified directly. And then it starts monitoring the buffers. When it hits the low threshold mark, it stops monitoring the buffers. In this way, you can set the buffers, the monitoring of the buffers, so you can have a proactive notification when the buffer starts to fill up. And of course, if this is a problem that happens a lot, you need to look into have deep buffers. CLI is sometimes, read always, useful. We have some, I want to highlight some features that are important or very good to have when you're troubleshooting on a per device basis. Mirror to CPU and mirror on drop. When you do a TCP dump in your device, you will only capture the traffic that goes to the CPU. With a mirror to CPU, you can basically start a mirroring session in your device and set the destination up to the CPU. So you can do a TCP dump of the traffic that you want by mirroring that traffic up to the CPU. Mirror and drop is when a feature which allows you to troubleshoot. And when you see you have drop packets, you want to understand what the packets, what flows you are dropping, or MPLS flows you are dropping. So that's a feature which you enable. When it occurs a drop, that will be sent to the control plane and then streamed to your management system. So you, or not management system, you can configure what the destination going to be. So it can be your laptop or anything. So those gives you good possibility to do device-based troubleshooting to find an issue quick. I'm not used to the clicker, obviously. S-flow. I know there are other kind of flows, but I use S-flow because that's an embedded technology in many of the switches. It's quite cost efficient. You need to have the switch with a S-flow built in, and also you need to have a collector. But if you F-flow, NetFlow, IPFix, or JFlow are really really good if you want to understand what applications are running in my network. What are the top talkers in my network? What are the top destinations in my network? So to give you an overview of what's actually running in my network. It's in the interbase. You can configure it per interface, and it sample the flows, it sample packets, and then it sends to the collector. So you can get nice graphs from source to destination, but you also get a wider information about what applications are running in my network. Flows are really good for the flow diagram. S-flow diagram includes a lot of information, like the source destination, the packet headers, QS information, VLAN information, etc. So you will get a lot of information from S-flow. This not only allows you to look at the flows, but you can see that the traffic actually confirms to the QS policy that you have in your network. You can see that you can build application dependency mappings. When I worked at Riverbed with just flow tools, we actually built an application map for one of the customers. Then we know exactly what ports that application was using. And we created a report and set an alert to that. If there were any other ports accessing in or out from that application, we could send an alert, like a security framework for that application. So, yeah, it gives you an overview of the flow of the traffic that runs in your network, but also you can drill down on a per flow basis. Back to the elephant. I talked about built-in features, the features that are built into the switches. Now we'll talk about a monitoring fabric. How can we get the network packet data? How do we get the network packet data out from the data center fabric and provide it to other tools like the NetScouts, like the Riverbeds, like the Kentic, as we have here today, who are great tools when it comes to analyze flows, analyze TCP, and do really good troubleshooting of that. So what we use is a network packet broker or a network packet broker fabric, which, well, actually, the easy part is connect the switches and to the ingress of the network packet broker, and egress will connect the tools and send the packets through. But network packet brokers add additional functionality. You can do deduplication. Of course, you can apply filtering on the ingress interfaces, because not all tools are interested in all traffic. You can do deduplication, packet slicing, you can do masking, you can use DPI to do application identification, and you can also, from the packet data, generate netflow and IPFix for the tools. And you want to be able to scale out your fabric. So this is, you can start small and build bigger when you get additional tools, or when you get like to connect additional switches. But one other thing that's important is not only the number of ports, it's the number of filters that you can apply to the ingress ports. Because if you run out of filters, you need to add additional switches. When looking at a packet broker fabric, one thing that you should look for is the number of filters that's supported, because you want to have a certain kind of traffic sent to the security tool, and then you will do a filter on that traffic and then send it out to multiple tools. So this is what a full-blown monitoring fabric can look like. You have the network packet broker functionality in the middle, which do the deduplication, the packet slicing, the NetFlow IPFix generation for NetScout tools, Kentic tools, security tools. To the left, you have your production network, which you connect of course, you connect every top of the rack switch, the leaf switches to the fabric, which allows you to capture the east-west traffic before it's encapsulated into VXLAN. The in and out traffic, I've used taps, optical taps here, but of course you can do span ports to mirror the traffic into the fabric also. And it's the same. Connect them to the ingress and do the work, the manipulation of the data before you send it to any of the tools to the right. One interesting thing that you should look at and talk about monitoring of the building a fabric for the data center network. But you probably have remote sites, remote data centers, and of course you can connect them also into the monitoring fabric using L2 GRE or something to capture traffic from those. So you have centralized tools which are extremely expensive. So you really want to use them for your complete infrastructure, for your complete network. So to summarize, look into the new features, built-in features that are in the modern switches today to support you with the troubleshooting. SNMP is not good enough anymore. And investigate how the different features can support you with and your team with troubleshooting. Talk to the other teams in your organization, the application performance team, the security team, to understand what kind of network data they want, and start to look into building a monitoring fabric to support the tools and, of course, your networking tools too. That will help you quicker identify issues and be proactive in your troubleshooting, and you will see the whole elephant. Thank you.
Do we have any questions for Henric? There's a question right at the back.
Thank you. I really support not using SNMP. So I have a question. Streaming telemetry and others is great. But you mentioned vendor-specific telemetry paths. What is your stability guarantee across versions?
I can only talk for our stability, of course, from Arista.
Sure.
But we do, and we deliver continuous streaming of telemetry from all our devices with in the same way. So I think we are very consistent in the way we do it. Of course, there will be, you can actually configure also what kind of what data you want to have streamed from each device.
Yeah, sure. But in this case, I'm talking about what is in the SNMP world, essentially a MIB update, where you would change a form. So, for example, another vendor that we used streaming telemetry for changed I think it was some counter that changed from being an integer to a string and then to a float between different versions, which required our monitoring. We had to reconfigure everything. So that's my question to you: are you treating this as an API, that it's stable? Like when you do it, and then you have a version 1 and 2 and 3 and so on?
No. We are consistent in that sense.
Okay, thank you.
Okay. Oh, you have a follow-up? Okay. Take the microphone back.
Yeah, I have 3 questions, but we don't have to do only me. So you mentioned the end-to-end latency, but you don't mention endpoint metrics like there is a reason we send these packets, right? And then they have buffers in the kernel, they have on the drivers, on the NIC. What's your thought on that?
That's a very good question, and from this point I was talking from a switch perspective. But of course there are agents that can do that kind of measurements. We don't provide any agents to server and so on. But
I mean, that's what people care about, right? Is that there is a reason we send these packets.
And that's why you also should be able to export the network data to the other teams that are working with applications or servers, so they can work with their data they get from the service and combine that with the network data to quickly combine to see the whole flow and be able to identify the we have some many of our vendors have integrations with VMware to get into the vSwitches, but still you're not on the host level in that sense. I know there are application performance like the App Dynamics, Cisco App Dynamics, and like the Dynatrace that are into the applications themselves that gives that granularity. But many of them don't get that granularity on the network. So I think it's a combination of the two that gives you the view of end-to-end latency from an application perspective.
Okay. We're out of time now, so please can you join me in thanking Henric for the presentation? Thank you so much.
Thanks.